When two forces F1 and F2 acting on a point, if F1 and F2 act in the same direction, the maximum resultant has a magnitude of 13 newtons. What are we saying? We're essentially saying that F1 plus F2 is equals to 13 newtons, right? And then the equation goes on to say that if F1 and F2 act in the opposite directions, the magnitude of the minimum resultant is 3 newton, right? So let's say, for instance, F2 is greater than F1, then we're going to have something like F2 minus F1 being equals to 3 newtons. That's what essentially we get in from the statement. And then the question now says that the magnitude of the two forces in Newton is, right? So right now we know that our first criteria, F1 plus F2 should be equals to 13 newtons. So let's go and look for two forces that can give us that before we look at the second option. So obviously here, if you look at A, we have 8 and 5, right? And we know fully well that 8 plus 5 is equals to 13 newtons. So A satisfy our first condition, and then B, 16 and 10, that cannot be true. And then for C, we have 3 and 10, which is also equals to 13, right? And then D, we have 10 and 7, which is definitely not true. So now we're just looking at A and C to find our answer, right? So let's look at our second criteria. We need F2 minus F1 to be equals to 13 newtons. So you can see for option A, if you say 8 minus 5, you're going to get 3 newtons. And then if you say 5 minus 8, you're going to get minus 3 newtons, right? We are only interested in the magnitude. So 8 and 5 clearly works. So our answer for 1.1 is going to be A. But let's also look at C and see if it can satisfy our equation. So for C, we have 3 and 10, right? Clearly, 10 minus 3 is equals to 7 newtons, and 3 minus 10 will be equals to minus 7. So only A satisfy our conditions. Now we can look at 1.2. 1.2 says that a free moving block slides down an inclined plane at a constant velocity. This means that then, before I even look at my options, with my eyes closed, I know fully well that if we're moving at constant velocity, right? So what is the consequence of constant velocity? The consequence of constant velocity is that acceleration is 0, right? But then, what is the consequence of an acceleration being equals to 0? F net is equals to ma. So if acceleration is equals to 0, then F net is equals to 0, right? Now I can look at my options, right? A says that the frictional force acting on the block is 0, right? There's no way we can tell with the information we have. That can be true, that cannot be true. We're not sure, right? And then for B, it says that the net force acting on the block is in the direction down the slope of the plane. The net force acting on the block is in the direction. If F net is equals to 0, we cannot really talk about the direction of that net force. And then for C, it says that the net force acting on the block is 0. And then like we have already stated, if the acceleration is 0, the F net is going to be 0. So our answer for 1.2 is going to be option C. Now let's look at 1.3. 1.3 says that a trolley is pushed along a horizontal surface with a force of 150 newtons at an angle of 45 degrees to the horizontal. The trolley experiences a constant frictional force of 60 newtons. And then our diagram clearly demonstrates that. And then we have few options there, 1, 2, 3, right, before the multiple choice itself. So they're saying that the net force acting on the trolley causes the trolley to accelerate horizontally, right, along the x-axis. That is true. Let me show you why I'm saying it's true. We know that F net will be equals to force applied along the x plus the frictional force, right? That's in the horizontal. So F applied along the x, that will be 150 multiplied by cos of 45, and then minus 60 degrees. Oh, not 60 degrees, but 60 newtons from the frictional force. So what is 150 multiplied by cos of 45? That is 106.06 minus 60, right? So clearly F net here is not 0, is greater than 0. So we're going to be accelerating along the horizontal, right? So our first option, I, is correct, right? Let's look at the second option. So we're saying that this option is correct. The second option is saying that the net force is equals to the applied force. That is not true, right? The net force is going to be 106 minus 60, which is going to be 46.06, somewhere there, right? So our second point is not true. Let's look at the third one. So we're saying this here is not true. The net force acting on the trolley is horizontally forward. That is true, right? Because it's positive, we're moving in the right direction. So here our options, so we're saying the first one and the third one are true, right? And that seems to be option C, right? So for 1.3, we are going with option C. So that's our answer for 1.3. Now let's go to 1.4. So 1.4 here is saying that a man in lift is moving upwards at a constant speed. The weight of the man is W. According to Newton's third law, the reaction force of the weight is the force of. So what you have to think of now is, why do we even experience weight, right? We just know that there's an equation, W is equals to M multiplied by G. But then, do you ever think about where this equation is coming from? Because we know fully well that if we're looking for G, the acceleration, right, that will be the capital letter G, and then the mass divided by r squared, right? So if we substitute that into W, you'll realize that we have G, mass 1, mass 2 divided by r squared, right? So this is the force between two bodies attracting each other. So we experience the weight because we are also exerting a force on the earth, right? So the reaction force of weight is the force of the man on the earth, and the reaction force of the man on the earth is the weight, right? So our answer for 1.4 will therefore be option D, right? The reaction force of the weight is the man on the earth. The reaction force of the man on the earth is the weight, right? And then let's do 1.6. 1.6 is saying 1.5, I meant. So 1.5 is saying the optical density of a medium, and then dot. So before we go any further, let's talk about the word optical density. So what are we talking about? We're talking about optical density, right? So optical density is directly proportional to refractive index, right? The higher the optical density of a medium, the higher the refractive index of that medium. So let's look at our option here. The optical density of a medium will be high if the refraction of light is less, right? That is clearly not true, because we're saying that the optical density is directly proportional to the refractive index of a medium. So A is incorrect. Now let's look at B. B is saying that the optical density of a medium is a measure of the refractive power of the medium, right? And that's exactly what I've been proposing. So for 1.5, we go in with option B. The optical density of a medium is a measure of the refractive power of that medium, right? And as a consequence, the higher the optical density, the higher the refractive index of that medium. And let's do 1.6. 1.6 is that in which one of the following graphs below will the gradient represent the refractive index of a material when light passes from air through the material? So obviously I'm not going to guess, right? We have graphs, so we need an equation, right? So we have light passing from one medium to another. So like we always do in this situation, we're going to need Snell's law. So what are we saying? We're saying that we're going from air to some medium, right? To some material that we don't really know. So if we use Snell's law, we're going to get Ni sine theta I being equals to Nr sine theta r. So we're going from air to some medium. We know fully well that the refractive index of air is 1. So if we substitute that, we're going to get 1 multiplied by sine of theta I being equals to Nr sine of theta r. Anything multiplied by 1 is just that thing, right? So we're going to get sine theta I being equals to Nr sine of theta r, right? And then you should be able to see here that we have y is equals to m, and then this becomes our x plus c, but then in this situation c0, right? So the gradient here is going to be the refractive index of the material, right? And then sine theta I is going to be on the y-axis, and sine theta r is going to be on the x-axis, right? And then if you look at our graphs here, that is option D. So 1.7 is saying that every point on a wave front acts as a point source of spherical secondary waves that move forward at the same speed as the wave. This statement represents, and then we have Snell's law. That is not Snell's law, obviously. And then for B, we have Huygens principle, right? And that's definitely what the definition says. So our answer for 1.7 is B. Just look up, the definition and the principle accompanying it, and you will realize that the answer for 1.7 is B. And then for 1.8, this is an interesting one, right? It's really easy, but yeah, it's interesting. Saying that 3 charges of magnitude plus 2q, plus 2q and minus 2q are shown in the sketch below, right? Which arrow currently represents the direction of the net force acting on the minus 2q charge? So let's pay our attention to the minus 2q charge, right? So here it is. Clearly it is negative, right? And then here we have plus 2q. So how does the positive charge interact with the negative charge? They attract each other, right? So the plus 2q charge will be pulling the minus 2q charge upwards, right? And then here we have minus 2q and plus 2q. So this one will be pulling it to the right because they're attracting each other, right? So you should see now that the resultant net force, right, will be somewhere there, right? And then which option is that? That is option A, right? And then now we can move forward and go to where we're going. We can move forward and go to 1.9. So we have 1.9. 1.9 is saying which one of the sketches below represents the correct magnetic field pattern around a straight current carrying conductor, right? So you should see that you probably haven't seen anything like C before, and that is not true, and D is also not true, right? The answer for 1.9 is actually B, right? Where am I saying the answer for 1.9? It's B. We're using a hand rule, and because of the format of the video, there's no way I can show you that, right? But then in the description of the video, I will put a link to a resource that can help you understand this concept better. And 1.10 says, which of the following graphs below correctly represents the relationship between potential difference and current in a non-ohmic resistor? So if the question was saying in an ohmic resistor, then the answer would be A, obviously, right? And then B, there's no way the voltage can be increasing and the current is going down, right? C, it looks like an ohmic resistor, but then you can see that instead of being a straight line, it's sort of, it's exponential, right? And then that's exactly what the graph of a non-ohmic resistor looks like. So our answer here for 1.10 is going to be C. So we have two forces that are acting at a point on a Cartesian plane, right? We have the 80 Newton force acting to the right and the 50 Newton force acting at an angle. And then 2.1 says, give a term for the following description, which says a single vector having the same effect as two or more vectors. We know fully well that that's a resultant vector, right? So you just write that and you get your 1 mark. And then we have 2.2 and 2.2.1 that says calculate the magnitude of the vertical component of the 50 Newton force. So we know fully well at this point that if we want to calculate the vertical component, which I'm denoting by the arrow, right, we take the force and multiply it by sine of the angle. And if the question was asking us to calculate the horizontal component, which I'm denoting again by the arrow, we'll take the force and multiply it by cos of the angle. So if we go ahead and do that, we're gonna have f of y being the vertical component is equals to the force multiplied by sine of the angle, like I'm saying, right? So we're gonna have 50 Newton multiplied by sine of 30 degrees. And then if you put that in your calculator, you're gonna get 25 Newton. And then moving ahead to 2.2.2, it says calculate the magnitude of the resultant force, right? So we know fully well that the resultant force squared is equals to the x component of the resultant force squared plus the y component of the resultant force squared. So let's go and look at the x components of the resultant force, right? So if we look at this, you will realize that we have the 80 Newton force that is pushing to the right, and then we have this component here which we have determined, which is pulling to the left. And then on our vertical axis, we only have the vertical component of the 50 Newton force. So up to so far, we can say that the resultant force squared is equals to r of x plus 25 Newton squared, right? Now the question becomes, what is r of x, right? That's what we basically supposed to calculate. So r of x will be equals to the 80 Newton force minus the x component of the 50 Newton force, right? Which will be f multiplied by cos of 30. So if we go ahead and do that, we're gonna get r of x is equals to 80 minus 50 multiplied by cos of 30, which will give you 36.7 Newton. So now in place of r of x, we can put 36.7 Newton. So we're gonna have r squared is equals to 36.7 Newton squared plus 25 squared. So we're gonna have r being equals to the square root of the 2, right? 36.7 plus 25 squared, which is equals to 44.441 Newton. And then you get your 5 marks. And then for 2.2.3, it says calculate the direction of the resultant net force. So when we calculate direction, there's 2 ways of doing it. Let me show you what I'm talking about. So we have already said that we have a vertical component, right? And then we have a horizontal component, and then we have our resultant. So for you to calculate the direction of the resultant force, you calculate it from either the vertical axis, the y-axis, or the x-axis. So you can calculate this angle here as your direction, or you can calculate this angle here as your direction, right? So in the name of the angle of inclination in math, we're gonna calculate from the x-axis to the resultant force, right? Because that's what we do when we want to calculate the angle of inclination in math. So I just want us to use something that we're gonna always use. So on your answer book, you're gonna put this sketch here, and you're gonna show that I'm actually calculating this angle here between the x-axis and the resultant force. So if you want to calculate that angle, you will use tan of theta equals to opposite divided by adjacent, right? So what is the adjacent? The adjacent is the x component, so it's 36.7, right? And then the opposite is the y, which you can put here, of 25 Newton, right? So you're gonna say tan theta is equals to the opposite, which is 25, divided by the adjacent, which is 36.7. So you're gonna have theta equals to tan arc of 25 divided by 36.7, being equals to 34.26 degrees. If you want to ask any questions or anything is not clear, or you have a video request, please just leave it in the comment, and as soon as I see it, I will respond accordingly. A box with a mass of 45 kg is pulled with a force of 90 Newton at an angle of 50 degrees to the horizontal. The box moves at a constant velocity. And then 3.1 says define the term kinetic frictional force. We know fully well that that's the force that opposes the motion of a moving object relative to a surface. The force that opposes the motion of a moving object relative to a surface. And then 3.2 says state Newton's first law of motion in words. It states that a body will remain in its state of rest or motion at a constant velocity unless a non-zero resultant force acts on it. A body will remain in its state of rest or motion at constant velocity unless a non-zero resultant force acts on it. And then 3.3 says calculate the magnitude of the horizontal component of the applied force. So on the applied force, we have the vertical component that points up, right, along the y-axis. And then we have the horizontal component that goes along the x-axis, right? If we wanna calculate the vertical component, we say the force multiplied by sine of the angle. And then if we want to determine the horizontal component, we'd say the force multiplied by cos of the angle. And then if we apply that same idea here, we're gonna get f of x, being the horizontal, right, is equals to the force multiplied by cos of theta. What is the force? The force is given as 90 newtons, and then the angle is given as 50 degrees. And then if you multiply 90 by cos of 50, you get 57.85 newton. We can move to 3.4. 3.4 says calculate the magnitude of the normal force. A lot of people think that it's very easy to calculate the normal force, but they usually get it wrong. So this is what's going on here. I want you to see something. So we have this 90 Newton force, right? If we resolve it about the y-axis and we get the vertical component, it will be pointing up like this, right? And we know fully well that gravity is acting on this object, so there is gravity pointing down. But that's not only the only forces acting on the y-axis. The other force that is acting on the y-axis is the normal force, right, which we are interested in. So we know that this box is moving at a constant velocity along the x-axis. Along the y-axis, there is no movement. So that tells us that the normal force plus the force applied perpendicular, the y component, is equals to Fg, right? Because these three forces are balancing each other. There's no movement along the y-axis. These two forces here are equals to this force that's pulling it down. So that's why there's no movement, right? So if you then want to calculate the normal force, you will say normal force equals to Fg minus Fa perpendicular, right? So now you know that Fg is the mass multiplied by 9.8, right? You will get 45 multiplied by 9.8 minus 90 multiplied by sine of 50 degrees. Why are we saying sine of 50 degrees? Because we said that if we wanna calculate the x component, we use cos like we did here, but then if we want the y component, we use sine. So if you punch that in your calculator, it's gonna give you 372.06 Newton, and that will be your normal force. And then 3.5 says calculate the coefficient of kinetic friction. So let me erase these forces that I've put here, and then I'll show you how we can solve this one. So if we resolve the 90 Newton force along the x-axis, it's gonna point in that way, right? It's gonna be pointing that way. And then we know that friction opposes the motion, so it's supposed to point in the opposite direction. But then our equation says that the box move at constant velocity, right? What does constant velocity tells us? It tells us that F net equals to ma, but because it's constant velocity, F net equals to 0. What is F net? F net is the addition of all forces that are acting on the object, right? So what are the forces acting on the object along the x-axis? It's f of x, fx, right, plus minus friction, right? Because we put minus for friction because it's opposing the movement, equals to 0. What does this tell us? This tells us that fx is equals to the friction, right? So in place of fx, we can put what we calculated in 3.3, which is 57.85. And then in place of friction, we can put the coefficient multiplied by the normal force, because we know fully well that friction is given by the coefficient multiplied by the normal force. This will then be equals to 57.85, and then this will be equals to the coefficient multiplied by the normal force, which we calculated in 3.4, right? We said that it is 372.06 Newton. Now we can divide both sides by 372.06, right? And that will give us a coefficient of 0.16. And then what's the SI unit of the coefficient? The SI unit of the coefficient is something we don't have, because we have the force in Newton and this normal force in Newton. So when you divide, the SI units cancel out, and as a result, we don't have an SI unit for the coefficient of kinetic friction or static friction, right? And then 3.6 says, will the coefficient of kinetic friction change if the angle of the applied force is decreased? Right? Yes or no, and give a reason. No, it's not gonna change, because when we define kinetic frictional force, we say that the force that opposes the motion of a moving object relative to a surface, not relative to the applied force or anything else. So if you want to change the coefficient of friction, you change the surface and nothing else. So no matter what else you change, the coefficient will stay the same. The coefficient only depends on the surface, on the material, and not anything else. So that's the reason you would give. Learners are investigating a relationship between the mass of an object and the acceleration it experiences when a constant net force is applied on the object. They use their results to draw the graph below. And then there is the graph on the left hand side. We have 1 divided by acceleration on the y-axis and mass in kg on the x-axis. And then 4.1 says state Newton's second law of motion in words. We know fully well that it states that when a resultant force acts on an object, the object will accelerate in the direction of the net force. That acceleration is directly proportional to the net force and inversely proportional to the net force. When a resultant force acts on an object, the object will accelerate in the direction of the net force. The acceleration is directly proportional to the net force and inversely proportional to the mass of the object. And then 4.2 says calculate the gradient of the graph, and then it says 3 marks. This is just 3 free marks because you're not applying any physics, you're just calculating the gradient. So to calculate the gradient, you're gonna pick any 2 points in the graph, right? And then calculate the gradient between the 2 points. So let's say we pick the point 0 and 0 here, and then we pick this point here, which is 0.25 and 0.5. So we're gonna have the gradient, right? M equals to y2 minus y1 divided by x2 minus x1. Even when you're calculating gradient in math, you're never gonna be awarded 3 marks. So let's go on, let's carry on and do what the question is asking of us. So y2, let's take 0.5, right? So we're gonna say 0.5 minus y1, which is 0, right? Minus 0 divided by x2, which is 0.25. So 0.25 minus 0. And then this will be equals to 0.5 divided by 0.25, which is obviously just 2. right? So if you take any other points, you're supposed to get the same thing. Let's say, for instance, you take this point here and this point. When you calculate the gradient, you will get the same exact thing. So it's just 3 free marks. And then let's do 4.3. 4.3 says to us, hence determine the net force applied on the object during the experiment, right? So for us to do that, we first have to determine what does the gradient of this graph give us. What does the gradient give us? Because we can see that on the y-axis we have 1 divided by a, and then on the x-axis we have the mass. So we use f net equals to ma to try and make sense of the gradient of the graph. So if we say f net equals to ma, this f net will be our y, right? But we don't want f net to be our y. We want a to be our y, because on our y we have 1 divided by a, right? So in order to achieve that, we're going to divide by m, and then we're going to divide by m. So as a result, we'll get a equals to f net divided by the mass. But on our y-axis, we have 1 divided by a, clearly, right? And then here we have a. So to do that, we can take every side to the power of -1, right? So if we say a to the -1 equals to f net divided by m to the -1, we're gonna get 1 divided by a equals to m divided by f net, right? So we can also write this as 1 divided by a equals to 1 divided by f net multiplied by m. We know fully well that in math, this can be y equals to mx plus c. Clearly, our y is 1 divided by a, our m is 1 divided by m net, and then our x is the mass, and then we don't have a c, right? Our c is 0. So we're gonna say the gradient is equals to 1 divided by f net. But what is the gradient? We know fully well that the gradient is 2 because we just calculated it. So if we cross multiply, we get f net multiplied by 2 equals to 1. So f net equals to 1 divided by 2 newtons, right? So in order to answer these kind of questions, you have to be able to play around with the formula and get what you want to get from it, right? In our case, our point was to get 1 divided by a as our y, and then we did exactly that. So in another case, that this might not be true. We might not be given 1 divided by a as our y. Maybe we might be given m as our y or something else, I don't know. But you have to be comfortable with playing around with the formula so that you can get what you want. And then 4.4 says, write down a conclusion for this experiment. Okay, so the conclusion of this experiment, look at this. So we know that f net equals to ma, right? And then if we make a the subject of the formula, we get f net divided by m, right? So here we can see that acceleration is inversely proportional to the mass. If you can say that, it would still be true, because that is true and you can deduce it from the graph. But then if you use 1 divided by a, you can see that as the mass increases, 1 divided by a increases. You can also say that 1 divided by a is directly proportional to the mass of an object. 1 divided by a is directly proportional to the mass of an object. I hope that makes sense. But if it doesn't, leave a comment and I will reply accordingly.
We have a crate of mass 25 kg sliding down on a plane which is inclined at 15 degrees to the horizontal. During the first part of the motion, from A to B, there is no friction between the crate and the plane, but part BC has a rough surface and is denoted there by some dotted lines. And then 5.1 says draw a free body diagram of all the forces acting on the crate while it moves from B to C. So from B to C is the part that has the friction, right? So if I draw the object there somewhere in BC, obviously we're gonna have the normal force acting perpendicular to the surface, right? Because that's how the normal force acts, perpendicular to a surface. And then we have FG pointing down, because as long as we are on a body, there's always going to be FG, whether we are on Earth, whether we are on Mars, like in question 6 of this question paper, there's always going to be FG. And then another force that is acting is friction, right? Like we are told. Friction opposes the direction of the motion. Thus, as a result, is pointing towards point A, right? Because that's where the object is coming from. So if we draw a free body diagram of all those forces, we're gonna have our free body there, and then the normal force, the FG, force due to the gravity, right? And then we're gonna have our frictional force, and with that we're gonna get our 3 marks. And now we can move to 5.2. 5.2 says calculate the magnitude of the acceleration of the crate while it moves from A to B. So the best way of solving this kind of problems, you have to draw a free body diagram first so that you can have a good understanding, a good idea of what's going on. So if we draw a free body diagram while it moves from A to B, we know that we have a normal force because it's resting on a surface, right? And then we have FG like we always do. But then in this case, we don't have gravity because from point A to... But in this case, we don't have friction because from point A to point B, the surface is said to be frictionless. So yeah, that's a good point to start. Now what we're gonna say is that F net equals to MA. And all the time when you're solving this kind of problems where you're supposed to count the acceleration, the tension, and all those kind of things, you're always gonna start by F net equals to MA. It's the same thing you're gonna do even when you're in grade 12. F net equals to MA. And then in place of F net, you put the biggest force that is acting on the body, right? And subtract all the small forces that are opposing the motion. But as you can see on this body of ours, we only have one force acting on the horizontally, which is FG parallel, right? Because for FG, we're gonna have FG parallel and FG perpendicular. So in place of F net, we're just gonna say FG parallel. If we had friction, then we're gonna say minus friction. And maybe if we had another box connected to that box, we're also gonna have minus tension. But for this case, we just have FG parallel. So we're gonna say that this FG parallel is equal to the mass of the object multiplied by the acceleration. And then in place of FG parallel, we can put the mass, right, which is 25 kg multiplied by 9,8 multiplied by sine of 15 degrees, because this here is FG. 25 multiplied by 9,8 is FG, right? It's the mass multiplied by the gravitational acceleration. And this part here, it gives us the parallel component of FG, right? If we were interested on the perpendicular component, we were gonna use cos, but then in this case, we are only interested on the parallel, so we are using sine. So this will be equals to, we know the mass of the object fully well, that is 25 kgs, right? So this will be equals to 25 and then multiply by the acceleration. What's the acceleration? It's what we are interested in, right? So now we're just solving for A. We are done with the physics, basically. We just have a math problem. So we're going to have the acceleration, which is equals to 25 multiplied by 9,8 multiplied by sine of 15 degrees divided by 25. And then if you put that in your calculator, you're gonna get A equals to 2.54 meters per second squared, right? And then you get your 4 marks. And now for 5.3, it says write down the direction of the acceleration of the crate while it slows down from B to C. The key phrase here is slows down, while it slows down, right? From B to C, right? Only up the slope or down the slope. So think about it. If an object is slowing down, it has a negative acceleration, or is decelerating, which is a term we don't really use in physics. But then if an object velocity is increasing or its speed is increasing, then the acceleration of the body is positive, right? Here we are told that it is slowing down, so its velocity or its speed is decreasing, right? It can only decrease if the acceleration is negative. And then as the object is moving down the slope, it only makes sense that if the acceleration is negative, it is up the slope, right? So the acceleration of this body is up the slope. And then for 5.4, it says we must the magnitude of the net acceleration from B to C is 1.2 meters per second, right? Per second squared. And then it says calculate the magnitude of the frictional force acting on the crate. So again, we know that the mass of the object is 25 kg, right? And that the acceleration is 1.2 meters per second squared. That's what they're telling us. And now we're supposed to calculate the magnitude of the frictional force acting on the crate. Do you have any idea how we're supposed to solve this? Yes, the idea you have is right. Again, we're gonna say F net equals to MA. It's very rare that you're gonna solve this kind of problems and not use F net equals to MA. Like, you're always gonna use this formula. Because now we know that from B to C there is frictional. Instead of just having FG parallel equals to MA like we did, this time we're gonna have FG parallel plus minus friction, right? Because friction is always opposing the direction of the motion. This is obviously equals to MA. This is our standard procedure. If you find yourself doing anything else other than this, you're doing something wrong. So what is FG? We know that FG is 25 multiplied by 9,8, and then the parallel component we're gonna multiply by sine of 15. Again, if we were looking for the perpendicular component, we're going to multiply by cos of 15 degrees, and then minus friction, right? Which is what we are interested in. And this will be equals to the mass of the object, which is 25 kg, right? Multiplied by an acceleration of 1.2 meters per second squared. And then what you have to realize here is that we have to substitute the acceleration with a negative sign, right? So that will give us minus 1.2. Why are we substituting it with a negative sign? Because in 5.3, we said that since the object is slowing down, the acceleration is up the slope, so it's opposite
to our direction of motion, right? If it's opposite to our direction of motion, we put a negative sign, just like we did with our friction. So we're gonna have minus friction is equals to 25 multiplied by minus 1.2, right? And then we're gonna subtract this whole expression here, right? So if we do that, we're gonna get minus 25 multiplied by 9,8 multiplied by sine of 15. So minus friction will be equals to minus 93.41 Newton. Just to write it largely, we will see this is friction being equals to 93.41 Newton. Every body in the universe attracts every other body with a gravitational force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. So essentially we're saying that F is equals to G M1 M2 divided by R squared, right? So if you write it like this, it becomes clear to see that every other body in the universe will attract every other body with a force that is directly proportional to the product of the body's masses and inversely proportional to the square distance between their centers. And then 6.2 is saying, let's calculate the mass of the probe. The gravitational force on a probe called Curiosity on the surface of Mars is 3,338 newtons. So we have F being equals to 3,338 newtons, and then it goes on to say that the radius of Mars is 3,390 kilometers. So we have R being equals to 3,390 kilometers, and then it goes on to say that the mass of the planet is 6.39 times 10 to the 23 kg. So we have the mass of Mars being equals to 6.39 times 10 to the 23. As you can see here, our radius is given in kilometers, right? And then we know fully well that in physics we deal with meters and not kilometers, right? So we just multiply this by 1,000 and we have our radius in meters. So which equation are we going to use to find the mass of the probe, right? We're going to use F is equals to G M1 M2 divided by R squared, right? Why are we using this formula? The variables that we have allow us to use this formula. Even 6.1 gives us a hint that we're supposed to use Newton's law of universal gravitation. So what is F? We've already established that F is 3,338 newtons. And then what is G? G is a constant, right? The gravitational acceleration. That is 6.67 times 10 to the minus 11 multiplied by the mass of Mars. The mass of Mars is 6.39 times 10 to the 23 multiplied by the mass of the probe. This is what we are looking for. And then we divide in by R squared, and that is 3,390 kilometers, right? We multiply by 1,000 so that we can convert it to meters, and we square. So now it's easy to see that the only variable we have here is the mass of the probe, right? So we're going to cross multiply in order to determine that mass. So we're going to have 3,338 multiplied by 3,390 multiplied by 1,000 being equals to so here you know that is the same as if we divide by 1, right? So we're going to have 6.67 times 10 to the minus 11 multiplied by 6.39 times 10 to the 23 m, right? So now it should be easy to see that we're going to divide both sides by the coefficient of m. and then we would have determined our mass. So if we do that, we're going to get the mass being equals to 3,338 multiplied by 3,390 multiplied by 1,000. And then now we're dividing everything by the coefficient of m, which is 6.67 times 10 to the minus 11 multiplied by 6.39 times 10 to the 23, right? And then if you put that in your calculator, you should get a mass of the probe, which is equals to 900 kgs, right? And then now we can do 6.3. So for 6.3 here, we're looking for the weight of the probe on Earth, right? So we're looking for the weight, and we know fully well that when we're looking for the weight, we say that the weight is equals to the mass multiplied by the acceleration on that body of interest, right? So we know the mass of the probe from 6.2, right? It's 9,000, and we know fully well the gravitational acceleration on the Earth, that is 9.8. So what are we saying here? We're going to have 900 being the mass, the gravitational acceleration, that is 9.8, right? And then if you put that in your calculator, you should get 8,820 newtons. So which phenomenon is described by the underlined words, right? The light ray changes direction every time it passes into a new medium. The light ray changes direction every time it passes into a new medium. We know fully well that is refraction. A light ray changes direction every time it passes through a new medium. And then 7.2 says, if the refractive index of water and air is 1.33 and 1 respectively. So what does respectively mean? For water, the refractive index is 1.33, and then for air, the refractive index is 1. So let's denote that in our sketch, right? For air, the refractive index is 1, and then for water is 1.33. Calculate the angle theta between the light ray and the surface of the water. So we want the angle between the light ray and the surface of the water. If the angle of refraction in the water is 40 degrees, the angle of refraction is 40 degrees. So fine, let's write our information down, right? So N incident, where is our light ray incident? It's incident on the air, right? And then the refractive index is 1. And then N refracted, the medium the light ray is moving into. We know that is water, right? And the refractive index is 1.33. And then we are given the refracted angle. So theta R for refracted, which is said to be 40 degrees. And then the question is saying, let's find the angle of incidence of the ray, right? So that's what we're looking for. It should be easy to see that we're going to use Snell's law, right? Which says that Ni sine theta of I is equals to Nr and sine theta of r. You can use n1 sine 1 is equals to n2 sine 2, whatever you're comfortable with, right? So what is the refractive index of the first medium? That is 1, right? We're coming from A. And then what is the angle? That's exactly what we're looking for. And then the refractive index of the medium we're moving into, that is water. The refractive index is 1.33. And then sine of theta, right? We're given the angle of the refractive ray relative to the normal. It is said to be 40 degrees. So now we can divide both sides by 1, right? When you divide both sides by 1, we're still gonna get whatever we have. So now we can basically say that theta, or the angle of incidence, will be equals to sine arc of 1.33 multiplied by sine of 40 degrees. And then if you put that in your calculator, you're gonna get 58 0.75 degrees. So what are we saying? Let's come to our sketch, right? This is the normal. We're saying that this angle here is 58.75, right? And then if we keep our normal going, this angle here, we are told that it is 40 degrees. Let's do 7.3. 7.3 is saying that the angle of refraction in the glass is 35 degrees. Calculate the refractive index of glass. So again, physics 101, right? We start by writing down the given information. So this angle of refraction from air to water will be the angle of incidence from water to glass, right? So now we know that the angle of incidence is equals to 40 degrees. And then we are given the angle of refraction, right? So the angle of refraction is equals to 35 degrees. What else do we know? We know the refractive index of water, right? We know that Ni is equals to 1.33. What we're looking for is Nr, which is our x, right? So again, if you apply Snell's law, we're gonna get Ni sine theta of I is equals to Nr sine theta of R. So what is Ni? We're coming from water, right? So it's 1.33. And then the angle is the angle of refraction from air to water, right? That is sine of 40 degrees. That will be equals to Nr, which is what we're looking for. And then the angle of refraction from water to glass is given to us as 35 degrees, right? So now we're going to say 1.33 multiplied by sine of 40 degrees divided by sine of 35 degrees is equals to Nr multiplied by sine of 35 degrees divided by sine of 35 degrees. We're solving for Nr, right? And then if you put this in your calculator, you're gonna get 1.49 is equals to Nr, right? So the refractive index of glass is 1.49, and then it makes total sense. We would like to think that the refractive index of water is greater than that of air, and the refractive index of glass is greater than that of water, right? Let's move to 7.4. So 7.4 is saying, draw the sketch below and complete the diagram of the path of the light ray from the air to the water to the glass. Show all the values of the angles of incidence, angles of refraction, and the normal in each medium. So let's just do that real quick, right? So we calculated the angle of incidence on the air, right? The angle of incidence on the air is not this theta here, right? We calculate the angle of incidence relative to the normal that I'm just constructing right now, right? We said that that angle is 58.75 degrees, right? And then that ray, it gets refracted when we move from air to water, right? And there goes our ray, right? Now we can construct our angle of refraction, right? The angle of refraction, it is given to us as 40 degrees. But then this angle of refraction from air to water will be our angle of incidence from water to glass, right? So if we construct a normal here, we should have an angle of 40 degrees from water to glass. And then again, when we move from water to glass, the ray will get refracted, right? The ray is getting refracted, and then now let's construct our normal and place our angle, right? The angle of refraction is between the ray and the normal and is given to us as 35 degrees. If we're moving to a new medium, then this angle of refraction will be the angle of incidence from the glass to the new medium. Now we can do 7.5. 7.5 is saying calculate the speed of light through the glass prism if the refractive index of glass is 1.5. We are given the refractive index of glass, it is said to be 1.5. But we know fully well that the refractive index is equals to the speed of light in vacuum divided by the speed of light in the medium of interest, right? Here we want the speed of light through the glass, right? So what is the refractive index? We know that that is 1.5. And then what is speed of light in vacuum? 3 times 10 to the 8 meters per second, right? Divided by the speed of light in the medium. So right now we're cross multiplying and dividing both sides by 1.5, right? We're gonna get the speed of light in the glass prism being equals to 3 times 10 to the 8 meters per second divided by 1.5. And then if you put that in your calculator, you're gonna get 2 times 10 to the 8 meters per second. 7.6 says that, is it possible that total internal reflection of the light ray can occur in the above situation, right? Only yes or no, right? So first thing first, what is total internal reflection? Total internal reflection is when a light ray gets inside a medium, right? And then it doesn't leave the medium. Let me show you a demonstration. So let's say this is our medium, right? And then we have a light ray coming in. If this light ray comes in and the angle of refraction is either 90 degrees or greater than, then the light ray won't leave that medium, right? If it's 90 degrees, then you can see that the light ray stays in the medium. And then if it is greater than 90 degrees, then the light ray actually gets reflected, right? And then you can see here in our diagram that we don't have any angle of refraction which is 90 degrees or greater than, right?
Since we don't have that, no total internal reflection will occur.
Write down an investigative question for this experiment. So now we have to read the statement, right? The statement says that an experiment is performed to investigate the effect of wavelength on the degree of diffraction, right? The experiment is performed to investigate the effect of wavelength on the degree of diffraction. So what investigative question can you pose for this experiment, right? What is the relationship between wavelength of a light ray and degree of diffraction? Or another way you can say, how does a change in wavelength affect the degree of diffraction, right? One between the two. You can also change a few words. But in the grand scheme of things, we are looking for the relationship between the wavelength of a light ray and the degree of diffraction, right? And that is 8.2. Now let's turn our attention to 8.3. So 8.3 is saying that the degree of diffraction is recorded for different colors of monochromatic light, and the results are shown on the graph below. On the y-axis, we have the degree of diffraction, and then on the x-axis, we have the wavelength, right? And then the question is saying, write the mathematical relationship between wavelength and the degree of diffraction. The mathematical relationship between wavelength and the degree of diffraction. We can see clearly from our graph, right, that the degree of diffraction is directly proportional to the wavelength, right? The degree of diffraction is directly proportional to the wavelength. So what you write for 8.3, you say that the degree of diffraction is directly proportional to the wavelength, right? As the wavelength increases, the degree of diffraction also increases, right? 8.4 is saying which color of light between red and green has the largest degree of diffraction? Which color of light between red and green has the largest degree of diffraction? Up to so far, we know that the degree of diffraction is directly proportional to the wavelength, right? We have red and green. So if we know the wavelength is between red and green, then we will know which one has the largest degree of diffraction. So between red and green, which color has the largest wavelength, right? Now we have to go to our visible light spectrum, right? We know that the trend goes like red, orange, yellow, green, blue, indigo, and violet. And the wavelength increases as we move to the left. So between red and green, red has the largest wavelength, right? So it is going to have the greatest degree of diffraction. So our answer for 8.4 is red, right? Our answer here is red. So if you are given different colors, let's say yellow and violet, then which one will have the largest degree of diffraction, right? We know fully well that yellow will have the largest degree of diffraction because it has a larger wavelength compared to violet. But what if you compare orange and blue, right? And then orange will have the highest degree of diffraction because it has a larger wavelength compared to blue. That's how you approach the question, right? And then for 8.5, they're saying that the experiment is repeated with only green light with a wavelength of 560 nanometers, but the slit width is changed and the degree of diffraction is recorded. Copy the set of x's below in your answer book and draw a graph showing the relationship between slit width and degree of diffraction. So now we need a relationship between degree of diffraction and slit width, right? So the degree of diffraction, we have already said that is directly proportional to the wavelength, right? But not only is it directly proportional to the wavelength, it is inversely proportional to the slit width, right? So when the slit width increases, the degree of diffraction decreases. So here on our graph, we should have something of this manner. You can see when the slit width is increasing, the degree of diffraction is decreasing. They're inversely proportional to each other. Coulomb's law in words, right? We know that F is equals to K Q1 Q2 divided by R squared. So from this equation here, we can see that the electrostatic force that one point charge will exert on another will be directly proportional to the product of their charges and inversely proportional to the square distance between them. So when you're in the exam and you don't remember the formula fully well, you just write down the equation and it becomes fully clear, right? The electrostatic force that one point charge will exert on another will be directly proportional to the product of their charges and inversely proportional to the square distance between them. Obviously, when you substitute the charges, you don't put the size, right? You just put the magnitude. And now we can do 9.2. 9.2 is saying, let's draw a vector diagram of the forces acting on sphere A indicate at least one angle. So let's look at sphere A, right? So sphere A is hanging from a string of negligible mass, right? And then is interacting with sphere B. So our sphere A here is positive, right? Here's the charge. And then sphere B is negative. Here's the charge, right? Minus 8 times 10 to the minus 9 coulombs. So how does a positive charge interact with a negative charge? They attract each other, right? So sphere B will be pulling sphere A to the left, and then sphere A will be pulling sphere B to the right. So if we draw in a vector diagram of the forces acting on sphere A, then we should have a vector that shows the electrostatic force that sphere B exerts on sphere A, right? And then apart from that, there's a gravitational force acting on sphere A, right? So we should have another vector pointing downwards, which we can name weight or FG. right? And then last but not least, we have the tension force from the string acting at an angle, right? So the tension force is stopping sphere A from falling down because of gravity, and then it's stopping sphere A from moving to the left, right? So this tension should look like this, right? And then there we have our tension force, and then they say we should include at least one angle. So you can just include the angle that is already there, which is 20 degrees, or you can put an angle here which is 70 degrees, right? And then now we have a vector diagram for sphere A, and we can go ahead and do 9.3. So 9.3 says that let's calculate the magnitude of the electrostatic force that sphere B exerts on sphere A, right? So again, we're saying that the electrostatic force is equals to K Q1 Q2 divided by R squared. Right? So we have the charges of Q1. Let's say Q1 is sphere A, right? So we know the charge of sphere A. We know the charge of the second sphere, charge B, right? And then we know K, that's a constant, right? And then now let's look for R squared. The distance between them is given as 3 centimeters. So we're going to say that R is equals to 3 centimeters divided by 100. We're converting it to meters, right? From centimeters to meters, you divide by 100. So now we can say that the electrostatic force will be equals to, so what is K? We know fully well that K is 9 times 10 to the power 9. And then the charge on Q1, right? We are only interested on the magnitude. We don't put the sign, right? So we're going to have 7 times 10 to the minus 9. And then Q2, which is sphere B, we're going to have 8 times 10 to the minus 9. We only put the magnitude and not the charge, divided by R squared, right? R, we say that is 3 centimeters. You convert it to meters by dividing by 100, and then you square. If you punch that in your calculator, you should get 5.6 times 10 to the what? To the minus 4 newtons, and that's the magnitude of the electrostatic force that sphere B exerts on A. It's also the magnitude of the electrostatic force that A exerts on B, right? Now let's do 9.4. 9.4 says, let's calculate the magnitude of the tension force in the string, right? So there's two ways of approaching this question, the magnitude of the tension force on the string, right? So again, our vector diagram for A, right? We had Fe, the electrostatic, and then we had Fg, and then we had the tension at an angle, right? We have already deduced that this angle here is 70 degrees. Why are we saying it's 70 degrees? The angle here is 20, the angle here is 90, so that angle here should be 70 degrees. So because the sphere A is not going up or down, right? The y component of the tension force should be balancing with Fg, right? But then still at the same time, the sphere A is not going to the left or to the right. So the x component of the tension force, right, should be balancing with the electrostatic force. So if you equate these two, you should be able to get the tension force. And then if you also equate these two, you should be able to get the tension force because they are balanced, right? But then let's do both. So let's equate the y component of the tension and Fg, right? So we have Ty being equals to Fg. So what is the tension force? We don't know what the tension force is. But then how do we find the y component? We multiply by sine of theta. We know that theta is 70 degrees, right? So we're going to have multiply by sine of 70 degrees being equals to Fg. Fg is the mass multiplied by the gravity, right? If you look at our equation here, we're told that the sphere has a mass of 0.2 grams, right? So we're going to have 0.2 divided by 1,000. Why are we dividing by 1,000? The SI unit of mass in physics is kgs, right? So we have to divide grams to 1,000 to convert to kg. Multiply by 9.8. So now we can say that the tension is equals to 0.2 divided by 1,000 multiplied by 9.8, and then everything divided by sine of 70 degrees. We just simply dividing both sides by 70 degrees, right? And the tension should be equals to 2.0857 times 10 to the minus 3 newtons, right? So we've used the first way to calculate it. Let's use the other. So the other way, we're saying that the x component of the tension will be equals to the electrostatic force, right? So now we're gonna have the tension multiplied by, if you want to find the x component, you take cos of the angle. So we have cos 70 being equals to the electrostatic force. We calculated the electrostatic force in 9.3, right? We know fully well that it is 7.13 times 10 to the minus 4, right? So now we divided both sides by cos of 70. So the tension is going to be 7.13 times 10 to the minus 4 divided by cos of 70, and that is equals to 2.0847 times 10 to the minus 3 newtons. As you can see here, we have 2 points P and T that are situated 3 millimeters apart in the electric field of positive charge Q as shown below. Yeah, it's easy to see. And then for 10.1, the question says that let's draw the electric field pattern around charge Q. Clearly, charge Q is positive, so the electric field lines should be radiating outwards, right? So in your answer book, we should see something of this manner. And then if it was the other way around and the charge Q was negative, then the electric field lines should be pointing towards the charge itself and not outside. Your electric field lines should be evenly separated and they should be of equal length, right? And then let's do 10.2. So we are told now that the magnitude of electric field at point P is 4 times 10 to the power 6 newtons per coulomb. So for the sake of clarity, let's just, write that down before we solve any problems. So we're saying that the electric field at P, right? So we're calling that EP, is equals to 4 times 10 to the 6 newtons per coulombs, right? And then at point T, the magnitude is 2.5 times 10 to the 5 newtons per coulomb. So again, for the sake of clarity, let's say ET, right, is equals to 2.5 times 10 to the power 5 newtons per coulomb. And then 10.2.1 says, let's calculate the ratio of the electric field at point P to the electric field at point T. Write the answer as EP is to ET. So let me make an example here. Let's say we had X is equals to 6 and Y is equals to, let's say Y is equals to 3, right? And we're saying that, let's find the ratio X is to Y. The ratio X is to Y, you will do the following. So you would say X is to Y. In place of X, you put in 6, and then in place of Y, you put in 3, right? But then you can see that you can divide both sides by 3, and then if you do that, you're gonna get 2 is to 1, and that's the ratio of X to Y. So we are applying the same idea here, right? We're saying that EP is to ET. But then what is EP? We know fully well that EP is 4 times 10 to the 6 newtons per coulomb. And then what is ET? That is 2.5 times 10 to the 5 newtons per coulomb, right? So we're dividing which number by which number here, because it's no longer straightforward, like for instance when you have 6 and 3, right? So we divide both number by the smallest. Clearly, between 4 times 10 to the 6 and 2.5 times 10 to the 5, 2.5 times 10 to the 5 is the smallest one. So we're going to divide by 2.5 times 10 to the 5 on both sides. So on the right hand side, we essentially dividing it by itself. So we should get 1, right? And then now we're going to say 4 times 10 to the 6 divided by 2.5 times 10 to the 5, right? That should give you 16. So EP is to ET has a ratio of 16 is to 1. And now let's do 10.2.2. 10.2.2 is a bit complicated. There's some math here that is involved, right? But let's see what we can do. So he's saying let's find the distance between charge Q and point P. Charge Q and point P, right? So let's see what we can do here. So obviously we can say EP is equals to KQ divided by R squared, right? That's the formula we have for the strength of an electric field at a given point, right? But then, lucky for us, we know fully well what EP is. EP is 4 times 10 to the power of 6, which is equals to K. K is a constant, that is 9 times 10 to the power 9. And then Q, at this point, we don't know the value of Q, right? So we'll just put it as it is. And then from Q to P, we don't know the distance. That's what we're looking for. So let's just put R squared, right? And then, yeah, you should be able to see now that we're stuck. We have 2 variables and 1 equation. So we need another equation. How can we find another equation? We can use point T. So let me show you what I'm talking about, right? So here, just to finish this off, let's cross multiply. If we cross multiply, we're gonna get 4 times 10 to the 6 multiplied by R squared is equals to 9 times 10 to the 9 multiplied by Q. And then we can call this our equation 1, right? And now to use point T, we're going to say that ET is equals to KQ divided by R squared. And then what is ET? We know fully well what ET is again, right? That is 2.5 times 10 to the 5 being equals to 9 times 10 to the 9. And then what is Q? We still don't know what Q is. And then now what is R squared? Now R squared is the distance from Q to T, right? We already established that the distance from Q to P is R, right? So QT should be R plus this 3 millimeters here, right? It's only fair. So we're gonna have R plus 3 millimeters, right? We don't deal with millimeters in physics, we deal with meters, so we have to divide that by 1,000. So we're gonna have 3 divided by 1,000 squared, right? Now you can see that we have 2 variables. We're gonna end up with 2 equations, and then we're gonna find R, right? Therefore, so if we cross multiply here, we should get 2.5 times 10 to the 5 multiplied by R plus 3 divided by 1,000 squared being equals to 9 times 10 to the power of 9 multiplied by Q. And then what are we calling this one? We're calling this one equation 2. So you can see that 9 times 10 to the 9 multiplied by Q is equals to this expression here. But then at the same time, 9 times 10 to the power of 9 multiplied by Q is equals to this expression here. So we can equate the 2 expressions. We're only going to have R as our variable, and we're going to try and solve that. So if we do that, we can say that equation 1 is equals to equation 2, obviously, because they're all equals to 9 times 10 to the 9 multiplied by Q. So equation 1 there was 4 times 10 to the 6 multiplied by r squared. Yes. And then our equation 2, we have 2.5 times 10 to the 5 multiplied by r plus 3 divided by 1,000 squared, right? So a lot of people, when they get to this step, they're going to solve this square here, right? But then if you do that, the problem becomes very complicated. So what I want you to do instead, you take square roots on both sides so that you don't have to square anything and end up having to solve a quadratic equation, right? So let me show you what I'm talking about. So we're going to take the square root on the left hand side, and we're also going to take the square root on the right hand side. If we do that, we're gonna get the square root of 4 times 10 to the power of 6 multiplied by, instead of r squared, now we just have r, right? And then on the right hand side, we're going to have the square root of 2.5 times 10 to the power of 5. And then instead, this square here that I'm circling right now is going to fall off, right? Because we're taking the square root. So we're just going to have r plus 3 divided by 1,000. And then we don't have the square root anymore, right? So now we're gonna multiply out the right hand side. After we multiply out the right hand side, we're just going to solve for r. So let me show you what I'm talking about. So we're gonna have the square root of 4 times 10 to the 6 multiplied by r being equals to the square root of 2.5 times 10 to the 5 multiplied by r plus the square root of 2.5 times 10 to the 5 multiplied by 3 divided by 1,000. So now we have r here, and then we have r here. We group in the like terms. So we're going to have 4 times 10 to the 6r minus the square root of 2.5 times 10 to the 5 r being equals to 2.5 times 10 to the 5 multiplied by 3 divided by 1,000. So I'm actually not going to put this in the calculator, right? I'm just going to take r as a common factor. So if I do that, I'm going to get 4 times 10 to the 6 minus 2.5 times 10 to the 5. R is a common factor, and this should be equals to the square root of 2.5 times 10 to the 5 multiplied by 3 divided by 1,000. I hope you're having as much fun watching this video as I'm having making it. So now I'm going to divide both sides by the coefficient of r, right? And then if I do that, I should get r is equals to the square root of 2.5 times 10 to the 5 multiplied by 3 divided by 1,000, right? And then now we're dividing by that coefficient, which is the square root of 4 times 10 to the 6 minus the square root of 2.5 times 10 to the 5. And then now you can finally put this expression in the calculator in attempt to find the final answer, right? And you should get 0.001 meters, right? That is also equals to 1 millimeter. So the distance between Q and point P is 1 millimeter, or 0.001 meters. And finally, to find the magnitude of charge Q, the magnitude of charge Q, right? We can use the electric field at P or at T, right? It doesn't matter right now because we have R. It should be easy to find Q, right? So let's just use EP. So we have EP is equals to, so we have KQ divided by R squared, right? But then EP is given to us. We know fully well that that is 4 times 10 to the 6 being equals to 9 times 10 to the 9 multiplied by Q. And then we divide in everything by 0.001 meters, right? 0.001 meters. and then we shouldn't forget to square. So now yeah, we can cross multiply. If you cross multiply, you get 4 times 10 to the 6 multiplied by 0.001 squared being equals to 9 times 10 to the 9 multiplied by q. You divide both sides by 9 times 10 to the 9, right? So you should get q is equals to 4.44 times 10 to the minus 10 coulombs. How do we calculate the change in the magnetic flux? So there's two ways of doing it, right? One way you can say that the change in the magnetic flux, right, will be given as the magnetic flux final minus the magnetic flux initial, right? That's one way of doing it. Another way of doing it, you can use the EMF induced in the coil, right? That will be the EMF is equals to minus n, being the number of turns in the coil, multiplied by the change in the magnetic flux divided by the change in time. So in the second formula, if you have the change in time, you have the number of terms, and you have the EMF induced, then you just solve for the change in the magnetic flux, right? So that's how you use the second formula. And then the first formula, this is how you use it. Let's say maybe we changed the angle, right? Then there's going to be a change in the magnetic flux, and consequently you'll be saying magnetic flux final minus magnetic flux initial to find that change, right? So in this question, let's look at the information we have and see which one of these two options we can go for. So here we are told that a square induction coil with a side of 3 centimeters. So before we go any further, we have a square induction coil with a side length of 3 centimeters, right? So now we know fully well that we have an area of that square, right, which we can calculate. And then it goes on to say the coil has 400 windings, right? So 400 windings, that's just another name for 400 turns. So we have n is equals to 400, right? And then it goes on to say that that coil is placed perpendicularly in a uniform magnetic field. What does perpendicularly in a uniform magnetic field tells us? It tells us that initially the angle was equals to 0, because if you place it perpendicularly in a magnetic field, then the induced EMF is at a maximum, right? So that angle should be equals to 0. And then it's rotated until we have an angle theta, which is equals to 45 degrees. So this will be our initial here, and this here will be our final. And that rotation, it takes a time of 0.08 second, right? So to find the change in the magnetic flux here, we're going to use the second formula, right? Because clearly we have the time here, we have the number of turns, and then let's see if we have the EMF, right? Because we need the EMF. Yeah, the question here also tells us that the EMF induced in the coil is 7 volts. So we can go ahead and use that formula. So for 11.2 here, we're going to say that the EMF will be equals to minus n, the number of turns on the coil, right? This is the formula we use, multiplied by the change in the magnetic flux divided by the change in time. So what is the EMF? The EMF is 7, right? And then how many number of turns do we have on the coil? We have 400 turns on the coil, and then we're looking for the change in the magnetic flux divided by the change in time. The time is 0.08 seconds, right? So let me put that in 0.08 seconds. So you can see here that we're going to cross multiply. If we do that, we're going to get minus 400 multiplied by the change in the magnetic flux being equals to 7 multiplied by 0.08. So the change in the magnetic flux will be equal to 7 multiplied by 0.08 divided by minus 400, right? So we're expecting a negative value there. And then if you put it in your calculator, you should get minus 1.4 times 10 to the minus 3 WB, right? That's Weber. And then we are done with 11.2. Now, what we need to do for 11.3 is to find the magnitude of the magnetic field. We want the magnitude of the magnetic field, right? So this is how we're going to do it. The symbol for the magnetic field is B, right? It's measured in Tesla, right? To find that magnetic field, we're going to use the change in the magnetic flux. Let me show you how. We say that the first formula you can use is this one right here, right? And then the second formula you can use is this one that involved EMF, which we just used, right? So we're going to use the first formula to find the magnitude of the magnetic field. So let me show you what we're talking about. So the change in the magnetic flux, we've already established that that is magnetic flux final minus magnetic flux initial. But then what you have to ask yourself is that how do we calculate magnetic flux initial and how do we calculate magnetic flux final, right? The formula for magnetic flux is equals to the magnetic field multiplied by the area and then cos of the angle, right? So the change in the magnetic flux will be equals to, so we have B multiplied by the area and then cos of theta final minus B magnetic field multiplied by the area cos of theta initial, right? This concept is a bit confusing if you're doing it for the first few times, so you might want to take the video back or go watch other videos that I've done on the topic. But anyway, stories in passing, right? What I want you to realize here is that we have the magnetic field and the area, magnetic field and the area, so we can pull that out as a common factor, right? I'm not so sure I'm allowed to say pull that out, but yeah, let's see what happens. So we have the change in the magnetic flux being equals to the magnetic field strength multiplied by the area and then multiplied by cos of theta final minus cos of theta initial. In place of the change in the magnetic flux, we're going to have minus 1.4 times 10 to the minus 3. That's what we just calculated in 11.2, right? That will be equals to the strength of the magnetic field, what we are looking for, and then the area. The area, we given the length of the side is 3 centimeters. We have a square, so length times breadth will just be side multiplied by side, right? But then the problem here, the length is given in centimeters, and we know fully well that in physics we are dealing with meters, right? So we have to convert that to meters by dividing by 100, right? And then multiply by 3 divided by 100. And then cos of theta final, right? So the final angle was 45 degrees. So we're going to have cos of 45 minus cos of 0, right? And then now you can see that the only variable we have is the strength of the magnetic field, right? So the physics is done. We're just solving the math now, right? And then how are we going to do that? We're going to divide both sides by the coefficient of the magnetic field. Let me show you what I'm talking about. So this will give us B, which is the strength of the magnetic field, being equals to minus 1.4 times 10 to the minus 3 divided by that coefficient there of the magnetic field, right? Which is 3 divided by 100 multiplied by 3 divided by 100, and then we have cos of 45 minus cos of 0, right? And then it turns out that if you put that in your calculator, you should get 5.31 T, right? Tesla. That's the SI unit of magnetic field. Now let's do 11.4, the interesting questions. The coil is now rotated through an angle of 45 degrees in a time of 0.05 seconds. Don't forget. Initially, we had rotated through an angle of 45 degrees at a time of 0.08 second, right? So from 0.08 second to 0.05 second. So now we're rotating it faster. What is the consequence of that as far as the induced EMF is concerned? Right, let's go to the formula. The EMF is equal to minus n, the number of turns on the coil, multiplied by the change in the magnetic flux, right? And then we divide that by time. So if you look at this equation, you should see that the EMF induced is inversely proportional to the time taken, right? So if you increase the time, you reduce the EMF. If you reduce the time, you increase the EMF. Clearly, here we're going from 0.08 to 0.05. So we're reducing the time. If we reduce the time, the induced EMF should increase. No questions asked, right? And then 11.5 says explain your answer to 11.4. We've done that, but you can just say that the EMF is inversely proportional to the time taken, right? So if the time increases, the EMF should go down. But in our case, the time is decreasing. So let's say delta t decreases. If delta t decreases, and then EMF should increase, right? And yeah, that's all we're saying essentially. Let's do 11.6. So 11.6 says the north pole of a bar magnet is pushed into a solenoid as shown in the sketch below, right? Clearly we have our bar magnet here, and then we are given the north pole, and if the north pole is on that end, then the south pole is in this end. No questions asked, right? And then now the question is saying that which pole will be induced at X, right only, north or south? So this is the trick. If you have a bar magnet and you are either pushing it into the coil or outside of the coil, right? Where you're pushing it in or where you're pulling it out, right? A pole that opposes the interaction will be induced. What am I saying? Let me show you what I'm saying. So let's say we're pushing it towards, right? So let's say we're pushing it towards, right? And then here we have the north, and then here we have the south, and then here we have the coil, right? If we're pushing it towards, the pole that will be induced here is the pole that opposes the motion. So because you're pushing it towards, a pole that pushes it away will be induced, right? So if we're pushing it towards and then we have the north pole, then here the north pole is gonna be induced so that it can push it away, right? So let's say we were pushing it away, right? So if we were pushing the magnet away, then a south pole would be induced because it's opposing the interaction, right? You're taking the magnet away, then a south pole will be induced so that it can pull it towards. So whatever you do with the magnet, a pole that opposes the interaction will be induced. So here, like we've said, we're pushing it towards, right? So a north pole will be induced so that it can opposes that interaction. And then for 11.7, it says that in which direction will the induced current flow, right? Only from A to B or from B to A. So if we have north on that end, we should have south to that end, right? This is positive, this is negative. The conventional flow of current is from positive to negative, right? So it will be flowing from A to B. 12.1 says calculate the value of resistor R if the total resistance of the circuit is 4.8 ohms. So we know that R total is equals to the resistance in series plus the resistance in parallel. So let's start with the resistance in series. When do we say that a resistor is in series? We say that a resistor is in series only if it gets undivided current. If it gets I total, it is in series, right? So
from our circuit here, we have the positive terminal and the negative terminal, right? And the current flows from the positive to the negative, but then it cannot bypass like this. It has to take the long route. So the current is going to take this path. It goes down this way, and then still going down, and then at this point it splits, right? Some proportion of the current will go in this direction, and another proportion of the current will go down in this direction, right? So let's just call this current IY, that is here, and then let's call the current that is here IX, and IX, and then at some point here IX and IY meets, and then we have I total again. Here we also have I total. So clearly there's no resistor that's gonna get I total. So for this circuit of ours, the resistance in total will be equals to 0 plus the resistance in parallel. So we're gonna have RT being equals to RP. So now we can look for the resistors in parallel and calculate that resistance as a consequence, right? So let me just erase some of this stuff I've put in here, and let's see how we can solve this problem. So we have already established that at this point the current splits, right? And then a proportion comes to this side. So this resistor here is getting a current IX, and then going down we have a proportion of the current, right, going in this direction. So these three resistors they get the same current IY, right? Because after this split here, the current is not splitting anywhere else. So the 3R resistor and the 2R resistor and the R resistor will get the same current. So these three here are getting the same current. So these three resistors are in series, but not say in series relative to the circuit, but relative to each other. So the resistance in this line here will be resistance equals to 3R plus 2R plus R, right? And then the resistance on the line on the top will just be R equals to 4R. So this resistance here is in parallel with this resistance here, and that's the resistance we have to calculate. So if we do that, we're gonna get RT equals to R1 multiplied by R2 divided by R1 plus R2. So what is RT? RT is 4.8, and then R1 is this resistance here, right, which is 4R, and then we multiply it by 3R plus 2R plus R, that will be 6R, right? So we have 6R divided by 4R plus 6R, so that will just be 10R. So now we have 4.8 being equals to 24 R squared divided by 10R. So R and R cancel out, so we're only left with 1R here. So we're gonna have 4.8 equals to 24R divided by 10. So if you solve this, you get R equals to 10 multiplied by 4.8 divided by 24. And then if you punch that in your calculator, you're gonna get R being equals to 2 ohms, and you have essentially solved your problem. And then now for 12.2, it says calculate the reading on the voltmeter if the current through the 4R resistor is 1.8 ohm. So fine, let me just erase this so that we can have some clarity, so to say. So we know that the current here I is equals to 1.8 amps, right? And then we're supposed to calculate the reading on this voltmeter here. So what do we know about resistors in parallel? We know that for the resistors in parallel, the voltage is the same, right? So if we calculate the voltage of this line, it will be equal to the voltage in this line too, right? So let's go ahead and do that. So we're gonna have V on the 4R resistor is equals to I multiplied by the resistance of 4R. So that will be equals to 1.8 multiplied by 4 multiplied by 2, because this resistor is 4R, right? And we know fully well that R is equals to 2. So if you say 1.8 multiplied by 4 multiplied by 2, that will give you 14.4 volts. So we know that the voltage on the line at the top, this line here is 14.4 volts, right? But because it's parallel to this line, then the voltage on this line will also be 14.4, because we know that for resistors in parallel, the voltage is the same, but the current is different. So, okay, fine. We have the voltage of the line on the bottom, right? Which is 14.4 volts. And then we don't have the current, right? But we have the resistance, because the resistance is 6R and R is equals to 2. So the resistance is essentially 12 ohms, right? So from this, we can then calculate the current on this line. If we calculate the current on this line, then it will be easy to determine the reading of the voltmeter. So let's go ahead and do that. We're going to have V equals to I multiplied by R. So 14.4 equals to I multiplied by 12. So we have I being equals to 14.4 divided by 12. So let me just 14.4 divided by 12. That is equals to 1.2 ohms, right? So 3R, 2R, and R are in series to each other, so their current is the same, right? So the current being experienced by this 2R resistor is also 1.2 ohms. So we can say the reading on the voltmeter, right, will be equals to I multiplied by R. What is I? I is 1.2, and then what is R? Is 2 multiplied by 2. So 1.2 multiplied by 2 multiplied by another 2, that is 4.8 volts. So the reading on the voltmeter will be 4.8 volts. Now let's move ahead and do 12.3. 12.3 says calculate the energy converted in resistor 4R in 2 minutes. We know here that the formula of the energy is given by W is equals to the power multiplied by the change in time. But the power can be equals to two things, right? The power will be equals to V squared divided by R, or I squared multiplied by R. So let's go ahead and look at the information we have for the 4R resistor, so that we can decide which formula to use. So if we go to 4R, then you will realize that we know the current. It is said to be 1.8 amps, right? So we're gonna use this formula of P. And then it says in 2 minutes. So we know fully well in physics we deal with seconds. So we're going to convert that 2 minutes to seconds essentially. So now we're going to have W being equals to I squared multiplied by R multiplied by the change in time. So what is I? I, we said, is 1.8. We square it, and then we multiply by 4, multiply by 2, because the value of R is 2, and then multiply by the 2 minutes, and then we multiply the 2 minutes by 60 to convert to seconds, right? And if you punch that in your calculator, you're gonna get the work being equals to 11036.8 joules, and then you are essentially done. And then for 12.4, we are told that the 4R resistor is replaced with an ammeter, right? So here we no longer have 4R, but we have some ammeter A. Here you have to know something. You have to know that the ammeter has a negligible resistance. So if you connect it in parallel, it's gonna short circuit your circuit, right? And then the question asks us, how will the reading on the voltmeter be influenced, right? Only increase, decrease, or stays the same? So let me show you what I mean when I say it will short circuit the circuit. So we have the current from the positive terminal, obviously flowing, and then there goes our current, there goes our current. At this point, if you replace the 4R resistor with an ammeter, the current will not go down. It will take the path with the least resistance. So it's gonna go down in this way, go down in this way, and then go up. So all these resistors, the 3R resistor, the 2R resistor, and then the R resistor, they will be left with no current. So basically the reading on the voltmeter will be 0, because you're gonna have V equals to I multiplied by R. I now is 0, so no matter what the resistance is, will just be equals to 0 volts, right? So you're coming from I think it's you're coming from 4.8 volts to 0 volts. So obviously that's a decrease. That's a decrease. And then 12.5 asks you to explain your answer in 12.4. And that's what I just explained. An ammeter has negligible resistance. So if you connect it in parallel, it's going to short circuit your circuit, right? So the other resistors won't get any current. Consequently, the 2R resistor is not getting any current.